right, last time we met, we studied something called arithmetic series, and I will give you a short little quiz, including one problem from that after the little lesson from today, which won't take that long. This is also about series, but it's about a series called geometric, and these are the only two we're going to study, with a little bit of an exception next week. So a series is geometric provided it has a multiplier. You recall last time we met, there was an adder, I called it, a common difference. Now it's going to be a common ratio, so that each term is obtained from the previous by multiplying by the same number every time. So here's an example. The first number can be anything, really. And then I have chosen to create this series, 5 plus 20 plus 80 plus 320. And if you study those four numbers, you probably will conclude that the rather obvious multiplier is 4, because 5 times 4 is 20, and 20 times 4 is 80, and 80 times 4 is 320. There are, mathematically speaking, lots of different things that it could be, but for our purposes here, we're going to go with what someone might call the obvious choice. So this goes all the way out to 81,920, and our goal is to add up all those numbers without writing them all out. The good news is, in some ways, this is actually easier than an arithmetic series, because it turns out that we don't have to know how many numbers there are in order to add them up. All right, so the multiplier is typically called R, and R stands for ratio, in the sense that one number other than 5 divided by the previous number. 20 divided by 5 is 4, 80 divided by 20 is 4, 320 divided by 80 is 4. So the common ratio is 4, as opposed to the common difference. But again, we're going to call the first term, in this case 5, a sub 1, and we're going to call the last term a sub n, and we need both of those in order to figure out what the total is, along with r. But those are the only three numbers that we need. We do not have to know how many numbers there are. Isn't that lovely? All right, so again, if capital A sub n is the sum of the first n terms in this geometric series, then here's the formula. Dun, 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 dun. A sub n, and this means multiply. A sub n r means a sub n times r minus a sub 1 divided by r minus 1. In words, it's the last number in the series times the multiplier minus the first number in the series, all that divided by the multiplier minus 1. Cool. So let's see. Well, the last number is 81,920. The multiplier is 4, so multiply it by 4, subtract 5, and then divide that by 4 minus 1, r minus 1. And you've got to do the numerator. And after you say minus 5, don't say divided by until you hit the equal sign, because if your calculator does the order of operations, if you just say that minus 5 divided by 3, it will do 5 divided by 3 and subtract that. Not good. So we use our calculator to figure out that that total is 109,222. It's not even 937 yet, and here we are adding up a whole bunch of numbers that total 109,000. This is some very powerful mathematics, and it has some wonderful applications, which I will show you maybe in a week or so. Okay, now it says if we happen to know the number of terms in the series, we can still use this formula, or we can choose a different one instead. This is the typical formula that people use when they assume that you know how many numbers there are. So that would be 5 times r to the n. Now I put 8 here. Why did I put 8? Where'd that come from? Well, here is an interesting example of intuition gone wild. When you start off with 5 and you multiply by 4 each time and you get up to 81,920, you might think that there are a whole bunch of numbers that are missing. And maybe there are. So let's just see how this goes. I'm just going to say 5 times 4, and then I'm going to say times, and then there's your 20. 4 times 4 times, oops, that's 320. Okay, so there's 4 terms, and 81,000 is the last one. So let's see what's missing. If I say 4, this is 1 missing, that's 1280. 2 missing, that's 5120. 3 missing, that's 20,480. And that one is, oh my God, there's only 8 numbers in that whole series. So we could sort of cheat and just add them all together because there's only 8 of them. Geometric series is an example of what you may hear in the news, things happening exponentially. And that's because of something I will show you here shortly. It turns out that sometimes we're going to have a multiplier that's between -1 and 1, like maybe 1/2 or 2/3. And when you have that, and you have r minus 1, you're going to have, like, for example, 1/3. If r is 1/3, 1/3 minus 1 is -2/3. And the numerator is also going to be negative. And sometimes we get bogged down in negative numbers. So it turns out that if your multiplier is between -1 and 1, you can use a different form of these. You notice here it's a sub n r minus a sub 1, and here it switches those, a sub 1 minus a sub n r, and instead of r minus 1, it's 1 minus r. It turns out that this allows us to not have so many negative numbers. Again, if r is 1/3, then 1 minus 1/3 is 2/3. At least it's positive. And the other, if you know how many numbers there are, as in this formula, you can switch those two. Or, this formula, instead of 4 to the 8th minus 1 and 4 minus 1, you can have 1 minus 4 to the 8th and 1 minus 4. But you wouldn't use that, this formula in that case. This is really more useful. Both of these are useful in case your r is between -1 and 1. Okay. Now on page 46, just like arithmetic series, geometric series can be written in sigma notation. So here's an example. And there'll be a little bit of a review in here. The sum from k equals 0 to 7 of 5 times 4 to the k, just like in the arithmetic series, your starting point is the number at the bottom, the lower limit, and you plug in 0. And when you plug in 0, you get 4 to the 0 power, and most people think that that's 0, but actually 4 to the 0 power is 1. In fact, any number to the 0 power is 1, other than 0 to the 0, which is not a number at all. All right, so the idea is to expand this, replace k with 0, 1, 2, 3, up to 7, and add the results. So here it is. 4 to the 0 is 1. 5 times 1 is 5. That's where the 5 comes from. Then you go up to 1. 4 to the 1 is 4. 5 times 4 is 20. 4 to the 2 is 16. 5 times 16 is 80. 4 to the 3 is 64, and 5 times 64 is 320, and so on. But we don't really need to write out all 8 of these numbers, because we have a formula that tells us all you need is the last number, the multiplier, and the first number. That's all you need. Okay, cool. So we do need the last number. Well, let's get our handy dandy calculator out. Now, in this case, it's going to be difficult if you don't have a scientific calculator. Now, they don't all look the same. On my calculator, on my computer, it has a button called x to the y power. And that means I'm going to do an exponent. So for example, if I wanted to do 4 to the 7th power, now this is 5 times 4 to the 7th, but I'm just going to do 4 raised to the power 7 equals. Now, some of you may have on your keyboard like an upside down V near the number 6 or above the number 6, like a shift 6 would be an upside down V. That's a caret. And that caret means, in many calculators, it means raised to the power. And others, I'd have to see them to help you out with that. But of course, you could just do 4 times 4 times 4 times 4 times 4 times 4 times 4, but that would be a little tedious. So after you do 4 to the k, then you multiply it by 5, and you get 81,920. Oh, really? Yeah, there it is, 81,920. Now, just so you'll know, if you have a scientific calculator, and you're supposed to have one for this course, but that doesn't mean you do have one. Likely you have one on your cell phone, just FYI. It turns out, if you remember order of operations, 5 times 4 to the 7th, for example, if I just put 5 times 4 raised to the 7th, it's going to raise 4 to the 7th power first, because exponents take priority over multiplication if there's no parentheses involved. So this is not 20 to the 7th. This is 5 times 4 to the 7th, and it's going to give us 81,920 again. So there it is. So now I go back to the formula, which says multiply that by the multiplier, then subtract the first term. So I'm going to multiply this, and again, the multiplier is 4. I'm going to multiply that by 4. And then I can just say minus, because it's going to multiply before it subtracts. I'm going to subtract the first number, which is 5. Now I got to say equals, because if I say divided by, it's going to divide 5 by something. So I'm going to say equals, and what that's divided by is, back to the formula, r minus 1. So my r is a multiplier. Now, you don't want to say 4 minus 1 unless you put it in parentheses, but I'm pretty sure you can do 4 minus 1 in your head. It's not that complicated. 4 minus 1 is 3. So I'm going to say divided by 3, and I get 109,225, which is, guess what? Same thing we got over here. Now, just so you'll know, if you want to, once you know that there's 8 numbers, you can do it this way. The first number times the multiplier to the n power minus 1 in parentheses. So with a calculator, to mimic that exactly, you would say 5 times, open parentheses, 4 raised to the power 8 minus 1, close parentheses, divided by 3, 109,225. Well, by golly, that worked there too. Unbelievable. All right. So at this point, I'm going to give you a little quiz. And when you're done with the quiz, please turn it in, and then come back to page 46 and work some of these.